Hi, we want to look at recursively defined functions and a little bit of sequence hodgepodge. We're going to get into some credit card examples and also some annuity problems. And so I've done this video before, but now I'm going to introduce this with the TI Nspire. So I'm going to try to use that new calculator. So what happens with a recursive formula, we've been calling this implicit in class, so you might hear either term, but then the nth term of the sequence is a function or has a relationship with the previous term. And you have a rule for this, and you also must have a starting point. And sometimes I call this the starting point the seed, because that's what we plant to determine what our function is. And so if I look at this example number 1, this notation might be a little bit weird for some of you. And some books might put a sub n plus 1 is equal to a sub n plus 3. But regardless what this means, and I can write this in here, this term right here is the term that I'm working with, a sub n. And so this is my now term. This is what I have right now. And then if I look at this one right here, this is what I call my previous term. And so I got now is equal to my previous term plus 3. So whatever I started off with would be my previous term, and then I'm going to add 3. Now I do this recursively, which means that I do it recurring. And so if I start this off, I'm going to start with my 7, and then it says my next term is going to be that 7 plus 3. So right now, this term right here is going to be 10. So if I label these things, this is my cell number 1, my cell number 2, my cell number 3, and so on. And so when I look at this thing right here, if I have my previous term being 10, I'm going to take 10 plus 3. That will give me my next term, which would be 13. And so what I call these are my locker numbers. So they're like lockers out in the hall, and then inside each locker I have these terms here. Now what some students want to do sometimes is they want to subtract 1 from these from what's inside the lockers. No, this n minus 1 is a subscript and just means the previous locker number. So if I say that n is equal to 3, that means n minus 1 was 2. And then this would be the term that's inside that locker 2, and this would be the term that's in locker number 3. And so that's all I'm doing. I'm just adding 3 each time. So that's my sequence. This could go on forever depending upon where we want to go with it. Okay? This one would be now is equal to 3 times the previous. And when I do that, so now I'm going to be multiplying. So my first term is 2, and then my next term is going to be 6, because I take the 3 times the 2, which would give me the 6. And then I'd have 18, and then I'd have 54. And then my locker numbers for these would be 1, 2, 3, and 4 there. Now looking in these two sequences, these are both sequences that we've dealt with before. So this one would be arithmetic because my common difference is 3 every time. And so I'd have D is equal to 3. This one, I have a product that I'm going to be multiplying by 3 each time. That's a little dot for a product, and so I'm going to multiply by 3 every time. And so this one would be geometric with my ratio being 3. And so you should be able to identify these by how they're set up. And in arithmetic, you're going to be adding every time, and in geometric, you're going to be multiplying every time. And then if you look down here, it says which are arithmetic, which are geometric. We've already explained why, and can you write an explicit formula for this? Just pause this and see if you can write a formula for this one. For me, it's the first plus n minus 1 times your difference, which would be 3. There's your equation. You can go ahead and simplify that. I'm not going to do that here. And then this one would be geometric. So then this would be your first term, which would be the 2, and you're going to be multiplying by 3 repetitively, and it's going to be raised to the n minus 1. Both these are based on n minus 1 because we have our starting value, and then this will be how many jumps of 3 that we take. This one, we're going to start with 2, and this would be how many jumps in a multiplicative sense that we're going to be taking after the 2. And that's why it's n minus 1 and not n. So if you look at this one, this was just positive 3 that we're adding, and this is 3 times. Now we have this one, which is called mixed. This is mixed recursion because I have both multiplication and subtraction. Now if we generate these terms, my first one would be 0. Now to plug in the next one, the 0 is the previous term, so then I would get negative 4. Now I take negative 4 and put it in there, negative 8, so this would be negative 12. And then I plug in negative 12 there. Negative 12 times 2 is negative 24. That would give me negative 28. So these are the first 4 terms of the sequence. Now if you notice, not arithmetic, because I don't have a common difference every time. And it's not geometric, because this one would be down by 4, this one would be down by 8, and this one would be down. I'm not multiplying here to get from one to the next. 4 times 3 gets me there. No, it just doesn't work. And so this is called mixed recursion, and we'll see if we're able to get to this and write equations for this. This one looks like it's a quadratic generator. A quadratic generator is going to be neither one of these, a geometric or an arithmetic. I'm going to get 1, and then I take the 1 and plug it in here, plus 1, which would give me 3. Then I take the 3 and plug it in here. This would be 3 squared, 9, plus 3, 12, 13. So to wrap these up, these are neither arithmetic nor geometric. Neither arithmetic nor geometric. This one you couldn't find a pattern for that one either. And that's partly because of the generator. This is a quadratic generator, so I'm going to assume that that's going to be something else. Okay, so now this one, let's try this one. This one tells me the first 2 terms, and so I need to find the next. And I think we've talked about this possibly in class, but it says that I take not just the first previous term, but I take the previous term. So if I want to find this third term, I'm going to take the one previous and the one previous to that and add them together. So I'm going to get 2. And then to go on to the next one, I take the 2 previous, so I'm going to get 3. I'm going to get 5. Add these 2 together, I'm going to get 8. I'm going to get 13. And possibly we've talked about this in class, but this is this Fibonacci sequence. This is a great one to look up and see what's going on with that. And you also can see a lot of things that go on with the golden ratio with that too. So this is kind of a fun one to investigate on your own. By the way, that's a neither. So looking at this pattern, and I guess we talked about it a little bit already, if we add, it's going to be arithmetic. If we multiply, it's going to be geometric, and then these are all something a little bit different. Okay, how about the handshake problem? If you walk into the room, how many handshakes are there if there's n people in the room? Remembering that just each person's going to shake hands with another person once. So if we can start off this problem, think about it a little bit and see if you can figure out how many handshakes there are with 5 people in a room. Okay, we're going to do this in class, so please remind me or whoever your teacher is that you're going to do the handshake problem in class. I think it just works better live. Okay, now we have these different sequences, and what we want to be able to do is find something that's called a fixed point of a recursive relationship. Now the fixed point does have some meaning in the in what we use it for as far as a credit card example, and I'll show you that in a little bit. So what a fixed point is that if my seed is planted such that each successive term is going to be that seed over and over again, then I have a fixed point. So in other words, if I have a sequence 4, 4, 4, 4, 4, 4, that would be a fixed point sequence. So what I want to do is find the fixed point of some function where I just give you the recursive formula. I didn't give you a seed because I don't know what seed is going to make this recursive formula. And notice that this is a mix that has multiplication and addition and subtraction in there. So first of all, if we let t1 equal 5, let's just try a seed and see what happens. So I'm going to start off with 5. I'm going to plug it in there, and I'm going to get 10 minus 3, which would be 7. And you can keep on doing these and you get 11, 19. You might want to pause and make sure that I'm doing that right. Go ahead and pause and take t1 equal to 6, plug it in here and see what happens. So in other words, I planted the seed 5, I got this sequence. Planted the seed 6, try it, pause. So this one turned out to be 6, 9, 15, 27. So based on the seed that I planted, it's going to vary my terms quite a bit. You think that, oh, it's going to be probably pretty close, but no, it changes quite a bit. Now, in this then, this is where this fixed point comes in. I want to know which point that I can plug in, or which seed I can plug in, so that I get the same number every time. Well, that means that now has to equal the previous. Yeah, every term equals the same. So to do that, what I let it is now equal to x and previous equal to x. They have to be the same value. So if I let x equal to 2x minus 3, I get that from right there. Now I solve this out, bring the x over, so I get x is equal to 3. This would be my fixed point. Now if you doubt me, take it and plug it in. So this is a seed that I'm looking for. So if I take 3 and plug it in there, it's going to be 2 times 3 minus 3. That would give me a 3. And it doesn't matter if I keep on plugging in 3 over and over again, it's still going to give me the same. So this sequence would be 3, 3, 3, 3, so on. So the fixed point is just the value that makes this repeat over and over again, same term. This is important when you're writing the equation of a mixed recursive formula as such. We might not get to all that in this class, but that is an important ingredient to writing the explicit formula. Okay, so here's a fixed point example. Credit card charges 18% annual interest. This is pretty much the norm. 18%, 20%, I don't know, you might even get more than that. Some of the lower ones might be 12%. I don't know what the lowest is, but I'm going to guess it's around 12. You owe $2,000 on the credit card, and you're going to pay, that got cut off, you're going to pay the minimum $50 per month. So we want to write a recurrence relationship for this. So what that means now is that my now is equal to my previous. So what's going to happen is that they're going to they're going to charge me 18% interest on the amount I owe, and then I'm going to pay off $50 of it. Now in the first month, sometimes they don't charge you the interest right away, but then they'll get you sooner or later. But this will be, and so these numbers don't always match up exactly what happens with the credit card, just based on do they charge you interest right away and different things like that, but it gives you a really solid idea of what's going on. So I take now is equal to the previous, and I'm going to multiply by the rate. The rate is going to be 1 plus, and this is just from your exponential growth problems that you did with exponential functions, and I'm going to divide by how many times they're going to apply this rate, and it's going to be 12 times. They're not charging me 18% per year. They're charging me 18%. They are charging me 18% per year, and so this will figure out what the interest rate they're going to apply each month for me. And then to finish this off, I'm going to be making a payment. So from my $2,000 that I owe, I'm going to take away $50. So even though I'm paying in, yeah, I'm taking it away from the $2,000 that I owe. This is a negative number, so I'm actually, I don't know how to say it exactly, but I'm adding this number into this negative number, and so I've got it kind of turned around a little bit. But this will work. And then I also need my first term, so a sub 1 is equal to 2,000. Now take out your calculator and have your TI Nspire ready for this. And you can do this on other calculators too. I have another video that does this with the 84, but I want to do it now with the Nspire. If you get a calculator screen up, you can put this recursive formula in. So I owed $2,000. They're going to charge me interest. This is going to bring the $2,000 back, and then this part is the add-on that the bank puts in, and then I'm going to subtract off $50, which is my payment. So after 1 month, I'm going to owe $1,980. Now what I can do with this too is that I can take the answer and I can multiply by this same thing, 1 plus 0.18 divided by 12, and then I'm going to subtract 50. And if I do this and keep on hitting enter, that's all I'm doing is hitting enter. If I use the ANS button at the original here, this can take down my balance and I can see what I owe after a certain amount of period of time. So this might be the first month, second month, third month, fourth month, and so on. Now there's a more elegant way to do this with the calculator too, and you can do it with the graphing menu. So I'm going to get a new page here, and I want to add graphs. And so when I add the graphs here, I go to the menu, and I'm going to change my input version for this graph. So I go to graph entry, and I'm going to go down here to where it says sequence, and I'm going to go back to sequence here. Now what this notation means is that this is like a sub n. The calculator doesn't do the subscript, and maybe that's the old calculator and they just put it into this new one too. So this just means the subscript. This is the locker number right here, and this is my function. Instead of using a, they're using u1. And so what happens now is that if I want to put this in, the same credit card problem, is that I'm going to go un1, I'm sorry, I did that wrong, u1 of, and then I want the previous. So the subscript would be n minus 1, and I put it in there, and then I'm going to multiply by, same thing, 1 plus 0.18, and I'm going to divide by 12, and then I want to subtract 50. So that's the same exact formula that I was working with before, except for this was the answer. So the answer is like the previous. And then my initial term would be 2,000. And step 1 is what we want. I mean, we're just doing it each month. So if I click on this, oh, I don't see anything. But I can go to fix my window. Remember, we had $2,000, and we want to see how long this will take to pay off. I don't know if that's your objective with credit cards, but it is my objective with credit cards. And so this is going to take me a lot of months. Maybe 100 months? No, that's way too many. Way, way, way too many. $50, I should be able to pay off that $2,000 TV pretty quick. And so this one I got to go up to 2,000 and maybe pad it a little bit, 20. And if I grab, oh, there it is. Oh, wow, that takes a long time to pay that off. So what's happening here is that each one of these payments, these are months as we go along here on the X. On the Y's, that's how much I'm going to be owing. So I start off with 2,000, and it will progressively decline here. However, wow, this takes a long time for me to cash out. Wow. Okay, so this is the recursive formula that we put in, and then here's how the payments go. Now we want to know what that value is. We can do this a couple ways. We can go to menu and go to table and then do my split screen table. And with this, these values are already in here. I want to look for when my balance is 0. And I find it right in there. So between the 62nd and the 63rd month. Uh-oh. That's like 5 years. I buy a TV and it takes me 5 years to pay it off because I'm paying the monthly on my credit card, the minimum monthly on my credit card. That is ridiculous. So we want to be able to pay a little bit more off as we can. So to answer the specific questions here, this is the second value through the sixth value of what I owe off my credit card. And then also here's where the payoff occurs between the 62nd and the 63rd month to answer this question here. Yeah, I try not to ever carry a balance on my credit card. It's always a bad idea. But having a credit card is all right from what we have. Now the fixed point for this one is if I go to my equation that I have over here, I'm going to do it over here. If I let my now equal to my previous, and I try to solve this out, when I solve this out, I'm going to find a decimal for this, and I'm going to subtract this x from this x over here, and then try to solve it. So I'm going to get all my x's on one side. So that's the value I get there. I'm going to get all my x's on one side. So this is 1x minus this times x, and so I'm going to be left with negative 0.015. X is equal to negative 50. So my fixed point would be the result of this, and this turns out to be my fixed point here, $3,333.33. What does that mean? Well, if it's a credit card, and I think if I have that balance, I think I'm going to owe that perpetually for the rest of my life if I'm just paying off the $50. Oh my. $3,300, pay the minimum. I'm going to be paying this off for the rest of my life and never make it, never dent it. That's not a good thing. So you got to be careful with credit cards when you have them. Now, in the rest of this worksheet, we'll probably have to do this in class because this is getting really long, and I apologize. But this is an annuity where you save money. So instead of subtracting $50, you're going to add in $200, and the interest rate's a little bit different. You might want to try that and see how that goes. Otherwise, we'll do that in class. All right, thanks a lot, and I hope you enjoyed this, and we'll get into some nice applications later. Thank you.